Part 2 of Unit 13 is about the common ion effect. Alright, the common ion effect is the extent of ionization of a weak electrolyte is decreased by adding to the solution a strong electrolyte that has an ion in common with the weak electrolyte. What that means for us when we're dealing with dissociation in Rice tables is that we have to pay attention to other ions that are present. We might have some of our products in a dissociation reaction that have an initial concentration of something besides 0. So let's take a look at this question. Calculate the fluoride ion concentration of a solution that is 0.2 molar in hydrofluoric acid and 0.1 molar in hydrochloric acid. And then they gave us the Ka for hydrofluoric acid. So since we're being asked to find the fluoride ion concentration, we're going to look at the dissociation reaction of hydrofluoric acid. HF plus water is going to be at equilibrium with the hydronium ion and fluoride ion. So our equilibrium expression that we're going to be using is Ka is equal to the hydronium concentration times the fluoride concentration divided by the equilibrium hydrofluoric acid concentration. We'll set up the Rice table and solve this on the next page. So here I've got my same equation given. Set up my Rice table on the side here, R, I, C, E. Remember that water doesn't do anything in a Rice table. My initial concentration of the hydrofluoric acid was 0.2. Now, typically over here, in problems we had been doing, we've just been putting in zeros for the initial concentrations of the products. But they told us that this solution was made with 0.1 molar hydrochloric acid. Well, remember, hydrochloric acid dissociates completely into a hydrogen ion and chloride, and that hydrogen ion immediately goes and forms a hydronium. So we've actually got some initial hydronium ion over here from that hydrochloric acid. It's 0.1, and we can plug our 0 in right here. We'd fill out the rest of the Rice table with x's, minus x. So at equilibrium we've got 0.2 minus x. We'd have plus x on the product side, so at equilibrium for hydronium it's 0.1 plus x, and plus x for fluoride, and at equilibrium fluoride is going to be x. Well, you saw the Ka value on the other page. We can use the weak acid assumption, so you would have to indicate that you were using the weak acid assumption by saying that 0.2 minus x is approximately equal to 0.2, and 0.1 plus x is approximately equal to 0.1. We can solve for x by just plugging these equilibrium values into our equilibrium expression. So our Ka value was 6.8 times 10 to the negative 4th. Our hydronium concentration is 0.1, multiply that by the fluoride concentration, and divide by the HF concentration of 0.2. When we solve this for x, we end up with x being equal to 1.4 times 10 to the negative 3rd. And that, if you go back to our Rice table, is the fluoride ion concentration. Now, if we'd done this as we have previous Rice tables, this would have been a 0 initially, and we would have had x squared divided by 0.2, or x squared divided by 0.2 is equal to Ka. So having the acid present in our initial solution caused us to have some hydronium at the beginning, which threw off our calculations through the rest of the problem. Let's look at another question. What is the pH of a solution made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make 1 liter of a solution? And then they gave us the Ka value for acetic acid. Well, let's write our dissociation reaction. Acetic acid is HC2H3O2. It's dissociating in water. And at equilibrium we'd have hydronium and the acetate ion. C2H3O2 minus. My initial concentrations, this is all in 1 liter, so we can just convert it to molarity. It's 0.3 molar acetic acid. Water doesn't do anything. There's no strong acid that this solution is made in, so we got a 0 here. Now, sodium acetate has the acetate ion in common. Sodium's not showing up in our dissociation reaction, it's just a spectator, but we do have some sodium acetate present, so this would actually be 0.3 over here. Through the rest of our Rice table, we have minus x, and plus x here. We'd have to indicate that we use the weak acid assumption again to have 0.3, x, and 0.3 again. So we could plug this into our equilibrium expression, which would be our Ka of 1.8 times 10 to the negative 5th is equal to 0.3 times x, the acetate and the hydronium, divided by the acetic acid concentration of 0.3. Well, this one's easy to do. The 0.3's cancel out, so x is equal to 1.8 times 10 to the negative 5th. That's my hydronium concentration. Well, the question asked me to find the pH, so I just have to take the negative log of the hydronium concentration. pH of this solution turns out to be 4.74. Now this pH is higher than the pH of just 0.3 molar acetic acid. When we had that sodium acetate present, that acetate ion present at the beginning, that causes a shift in the reaction. Le Chatelier's principle says that if you add something to the right side of a reaction, it's going to shift to the left to get rid of that stress. So adding that product ion caused the reaction to shift back to the left, which meant less dissociation of the acetic acid or less production of the hydronium ions. If we didn't have the sodium acetate, it would have been x squared divided by 0.3. X would have been a little bit higher. Our pH would have been a little bit more acidic. But since we had that sodium acetate present at the beginning, it decreased the hydronium concentration by causing a shift in Le Chatelier's principle, shifted the reaction to the left, and caused us to have a higher or more basic pH. Your question for this section: nitrous acid has a Ka of 7.2 times 10 to the negative 4th. Calculate the pH of a solution that is 0.5 molar nitrous acid and 0.25 molar potassium nitrite.